This video covers measurement methods for linear viscoelastic materials for polymer rheology and processing. When you're talking about relationship between the functions that we've looked at this point, despite the complexity or the simplicity of the particular model, these relationships are not independent. Experimental data from linear viscoelastic experiments are presented in the form of graphs of components of dynamic parameters. And this is typically during an experiment in which you're measuring rheological response. So these types of measurements include static and dynamic. In static types of measurement, you're in position of a step change. This might be a stress or a strain. And then you're observing the subsequent development in time, and that might be stress or strain. In dynamic, you're applying an application of harmonically varying strain. For the static methods, the first type is a creep test at constant stress, and there are relaxation tests at constant strain. The input is considered to be applied instantaneously, whether that be stress or strain, an increase or a decrease. In practice, this is obviously not actually true. You have inertia, you have a delay in transmitting a signal, but the time required for the signal must be short compared to the overall experimentation time. This limits the methods to materials with a short or a few seconds of relaxation time. So, how do you do a test? We're going to break it down. In this case, is a static viscoelastic experiment. First, you have to determine sample geometry. If you have solids, those can be made into strips or dog bones or something like that. Liquid samples using rheometers are similar to those discussed for viscosity measurement. You have to determine a way of securing the sample. You have to apply an input signal, and then you have to measure and record an output signal. Very simple. Typically, you're applying an input signal and measuring an output signal with some sort of electronic device. It is easier to measure strain. Strain is where you're deforming a sample, and that's easier to measure. Creep testing is much more common than relaxation testing. In relaxation testing, you'd be measuring the stress, and that's harder to do. So here you have a static creep curve. So the strain is on the y-axis, applied over a period of time. So applied at time 0 and removed at time 1, and you see the strain developing and then relaxing. So strain is plotted against time. Constant stress is applied at time 0. The stress is removed at time 1. You have different regions of this particular curve. So the instantaneous region is 0 to get to strain 1. Retardation is strain 1 to strain 2, and then you have constant strain rate at strain 2 to strain 3. And this is shown here. So you have your instantaneous portion here, which is linear, and you have your retardation portion here, and then you have constant strain. This is also linear in its relationship, and then upon the stress removal. Instantaneous strains on loading and unloading are equal. The ratio of the stress to the instantaneous strain is independent of stress, and the constant rate strain from gamma 2 to gamma 3 is not recovered. Here you have a stress relaxation curve. So here you're applying stress on the y-axis. Here a strain is applied and develops, and the strain is then reversed. So you have actually goes to the negative y-axis over time. In this case, stress is plotted against time. You have instantaneous changes in stress, which are equal. So 0 to stress 1 and stress 2 to stress 3. The ratio of the instantaneous stress to strain is independent of strain. Incomplete relaxation at time 1 may indicate that further relaxation should occur at a longer time, or material at low deformation behaves like a Hookean solid, and then you'd have residual stress that would persist indefinitely. Typically, this is not the type of mechanical curve that you look at. Typically, this is the type of mechanical curve, or static creep curve. When you're talking about dynamic viscoelastic measurement methods, you're talking about oscillatory strain, wave propagation, or steady flow. When it comes to oscillatory strain, these methods have increased considerably, and this is through the development of rheogoniometers. A goniometer is an instrument that either measures an angle or allows an object to be rotated to a precise angular position. A rheogoniometer is a type of rheometer that can be used to determine the viscous and elastic flow properties of a fluid. Processing of input and output signals to give in-phase and out-of-phase components directly is used in this case, and display components of modulus and functions of oscillatory frequency. When you're looking at an instrument that does oscillatory strain, you have an instrument that can cover a very wide frequency range, 10 to the negative 3 to 10 to the 3 inverse seconds. The material, it must have a broad spectrum of relaxation times. Time spectrum of 10 to the negative 3 to 10 to the 3 seconds, that's about 20 minutes, can be covered. If longer times, so 10 to the 4th, that's about 3 hours. Typically you'd want to do a static test instead of a more dynamic test. There are advantages and disadvantages to this type of measurement method. The advantages are conventional tensor or shear geometries, and they're readily adaptable to torsion deformations with solid-like materials. The disadvantage is the frequency range is only over 2 orders of magnitude, and if you get liquid-like material, it's not typically used for this sort of thing. Forced oscillatory strain is done frequently using the type of geometries that we saw with viscometers through forced oscillations. You have cone and plate, parallel plate, and concentric cylinder. Typically the experiments that occur in my lab are parallel plate with a sort of paste material. The bottom or the outside part goes through forced oscillations about its axis. Motion is transmitted through the material to the top or outside part, and the amplitude and phase lag are what are actually being measured in this case. So this consists of 2 plates that are characterized by the plate radius and the distance between the plate. The material to be tested is applied between the plates, and the top plate oscillates at a constant frequency throughout the test. The material experiences sinusoidal shear deformation, and the stress response is measured by the torque on the top plate. Viscous behavior is characterized by the storage modulus, G prime, and the loss modulus, G double prime. If you're measuring yield stress for these materials, it's determined by the point at which G prime and G double prime cross over one another. So, R sub P is the radius of the plate, and then H is the distance between the plates. So the one that I use is a 40 millimeter parallel plate with a 1 millimeter gap, and we produce curves that look like this, and we look at the shear stress, which is this point here. This is a cone and plate apparatus. This is used to determine dynamic viscosity and dynamic rigidity. Dynamic viscosity is eta prime and dynamic rigidity is G prime. And these are functions of imposed frequency. So it has a very similar look to the parallel plate. It oscillates around this axis here, but with a cone type geometry rather than a parallel plate. Steady flow is another type of dynamic experiment. In other methods, the parts of the measurement apparatus itself oscillate, and this creates unsteady flow. Steady flow instruments are based on a different principle. As is implied by the name, the flow is steady. The velocity at a fixed point in the apparatus is unchanging, and the rheometer is constructed in a way that the fluid elements themselves undergo oscillatory shear, and not the elements of the apparatus. So here's an example of steady flow. There's 2 parallel circular plates separated by a distance h here. So separated by this distance, that represents h. They're mounted on a parallel axis offset by a distance. So the distance is between this axis and this axis. So this distance here, d. One spindle is rotated at a constant angular velocity. The other spindle is free to rotate and takes a velocity similar to the first. The fluid elements themselves, so the material between the two, is exposed to sinusoidal shear, and the force on each plate can be related to dynamic viscosity and dynamic rigidity. This is similar to oscillatory rheology in that the test consists of 2 plates that are characterized by the radius and the distance. The material to be tested is applied between the plates, and the top plate continuously rotates in one direction. The top plate produces a constant steady shear stress to obtain the maximum shear rate range for the possible material, and it produces a relationship shown here, where you have viscosity is equal to tau over gamma. This equals viscosity. This is shear stress, which is constant, and this produces shear rate. Wave propagation is the other type. In this case, waves are generated at the surface of a specimen. The specimen is in contact with a wave generator, and this allows for evaluation of viscoelastic functions, the measurement of wave velocity through the specimen, and measurement of attenuation through the specimen. And this can be adapted to high-frequency studies, so kilohertz up to a few hundred gigahertz. This is studying liquids that behave in a Newtonian manner on other rheometers. So you can see viscoelastic behavior from these on other types of measurement methods. Here you can, here where they would be Newtonian. This allows for molecular weight below 1,000 grams per mole in non-polymeric liquids. Not typically appropriate for polymeric type specimens. And this concludes measurement methods of viscoelastic materials. Thank you.